Section 4.3, Types of Zeros. Polynomials can have rational, irrational, and/or imaginary zeros. For example, classify the zeros in the following polynomial function. Notice f of x is in factored form. So to find the zeros, we simply set each factor equal to 0 and solve for x. So let's work on identifying the zeros from left to right. If I set x cubed equal to 0 and I solve for x, I'm going to get the 0 x equals 0. 0 is a rational number. Now, just as a reminder, rational numbers can be written as a fraction. Irrational numbers cannot be written as a fraction. So, rational numbers include integers, fractions, terminating decimals, whereas irrational numbers contain non-terminating, non-repeating decimals or square roots that cannot be simplified, for example. So x equals 0 is a rational number. Now, as we go, let's also observe multiplicity because the exponent there is 3. This particular rational 0 has multiplicity of 3. Looking at our next factor, if we set that equal to 0 and solve for x, we're going to get the 0 x equals 2 because 2 can be written as a fraction. It is also a rational 0. Note that the exponent on the factor from which it came is 1, so it has multiplicity 1. Working on our next factor here, setting it equal to 0 and solving for x, we'd end up with the fraction negative 1/3. This is also a rational 0. Observing that that factor repeats twice, we know this particular 0 has a multiplicity of 2. Now, moving to our next factor, it looks a little more complicated. If I were to set that equal to 0 and solve for x, I would end up with the 0 square root of 5. Square root of 5 cannot be simplified. It cannot be written as a fraction. So this is an example of an irrational 0. But in this case, it has a multiplicity of 1. Working on our next factor, setting it equal to 0 and solving for x, we would get negative square root of 5. Again, this is an irrational number, and that factor repeats once, so this 0 has multiplicity of 1. Notice how the last factor is different. The other factors that we were dealing with had an x to the power of 1, but this has x to the power of 2. This is a quadratic factor. That means it contains 2 zeros. It cannot be factored further because it is the sum of 2 squares, not the difference of 2 squares. So to find the zeros, I'm going to have to work a little harder on this one. If I set the factor equal to 0, we notice we have a quadratic equation that we could solve using the square root property. So taking the square root of both sides, notice we end up with x equals plus or minus 2i. That was a negative 4 in there. So we get 2 zeros out of this factor, plus or minus 2i. Those are imaginary or complex zeros. Each of those has a multiplicity of 1. So, all things considered, this polynomial, which thank goodness it was in factored form, has 1, 2, 3, 4, 5, 6, 7 distinct zeros, if I count both of those imaginary zeros. However, if we sum the multiplicities, we would end up with 3, 4, 5, 6, 7, 8, 9, 10. This would be a degree 10 polynomial. So it's degree 10. It has 7 distinct zeros. Some of them are rational, that is, they can be written as a fraction. Some of them are irrational, that is, they cannot be written as a fraction. And some of them are imaginary. When we solve a polynomial equation of higher degree, we have to keep that in mind, that there are potentially many different types of zeros. In practice, we find the easy ones first. We're going to find the rational zeros using synthetic division. We're going to reduce the polynomial down far enough to discover the irrational and imaginary zeros. So in section 4.3.1, we will focus on those rational zeros. Example 1. graph the given polynomial function with your graphing calculator. Determine a 0 from the graph. Remember, a 0 corresponds to an x-intercept. And confirm it with synthetic division. That means I'm going to divide it out using synthetic division, and I'm looking for a remainder of 0. Then find all remaining zeros and list all zeros in your answer. So on example A, we have the polynomial function f of x equals x cubed minus x squared minus 10x minus 8. Notice this is a degree 3 polynomial. Again, we're recognizing that the highest polynomial. We are recognizing that the highest exponent on an x that we can find is 3. Therefore, it is a degree 3 polynomial. So this means we can expect at most 3 zeros. They may or may not repeat, and they can be rational, irrational, or complex. Now, in the previous section, we started with a particular k value. We were able to find zeros given 1 0. In this case, we have no idea what any of the zeros are, and this polynomial cannot be factored by grouping. So to get started, we are going to graph the polynomial function with our calculator. So I'm going to go to my y equals function and type in the polynomial as it is written. X cubed minus x squared minus 10x minus 8. And I'm going to graph that in our standard viewing window. Remember, zeros correspond to x-intercepts. So we're using our calculator to determine an educated guess about one of the zeros. I'm going to use the one on the right. Looks like it crosses at x equals 4. Now, it appears to be 4 on the calculator, but it might be 4.001. So again, the calculator gives us an educated guess for a place to begin, but I do need to confirm that it is in fact a 0 using the synthetic division process. So I'm going to use the 0, x equals 4. I'm going to pick up the coefficients of the given polynomial and set up my synthetic division problem. So remember, we take the number in the box times the number on the baseline, and then we sum vertically. So 4 times 3 gives me 12. Negative 10 plus 12 is 2. 4 times 2 is 8, and negative 8 plus 8 is 0. So we have a remainder of 0. Therefore, we know at this point, x equals 4 is a 0. Now, we started out with a degree 3 polynomial. After one round of synthetic division, this would represent a degree 2 polynomial. So it is encoding 2 more zeros. If we glance back at the graphing calculator, notice there's another x-intercept at negative 1. I could divide negative 1 out of the original polynomial, or I could just tack it on to this degree polynomial that I have listed right here. So I'm going to continue my synthetic division process using this degree 2 polynomial, stopping short of the remainder. So the process is the same. Bring down your first term, multiply and add, multiply and add. So since we ended up with a remainder of 0, we can make the observation x equals negative 1 is also a 0. So after this extra round of synthetic division, this would represent a degree 1 polynomial. So after each round of synthetic division, the degree decreases by 1. So that means there's one more 0 to find. If I look at the calculator and observe the last x-intercept there is negative 2, I can divide negative 2 out of this. It's called a depressed polynomial by stopping short of that remainder. So notice by getting a remainder 0 here, that confirms that x equals negative 2 is also a 0. So we can present our answer. We can say that the zeros of this polynomial in a set, and I'm going to order them least to greatest, negative 2, negative 1, and 4, are the zeros of this polynomial. Remember, we started with a degree 3 polynomial. We expected at most 3 zeros, and we obtained exactly 3 zeros. That means each of those zeros has multiplicity of 1. We can also confirm that by noticing that the graph crosses the x-axis at each one of those zeros. Remember, the graph crosses at a zero of odd multiplicity. So we just solved a degree 3 polynomial equation. Thinking of starting the semester with simple linear equations, you may have never thought that we'd arrive at equations like this, but they are actually pretty easy. All right, let's practice that again. In this case, we are looking at another degree 3 polynomial. That's always a good thing to notice because it tells me I should expect at most 3 zeros. Remember, if possible, you can solve with factoring by grouping, but this particular polynomial would not factor by grouping. So we're going to use our calculator and the combination of synthetic division to find the 3 zeros of this polynomial function. So I'm going to take some time and type it into the y equals function in my calculator and observe it in the standard viewing window. Remember, you can do zoom number 6 to make sure you end in the standard viewing window. So we want to observe where the graph crosses the x-axis. I notice at x equals 1, it is passing through the x-axis. So we can make the hypothesis that 1 is a 0, and we can, of course, confirm that by synthetic division. Now, on the left side, I'm a little bit unsure. We can zoom in, zoom number 2, and then press enter to get a little more insight on what's going on over there on the left side. Looks like clearly -2 is going to be a 0 and possibly 1/2 or -1.5 for our next 0. But let's get the easy ones out of the way first. I'm going to start with the rightmost x-intercept, which is x equals 1. And I want to confirm that it is a 0 using the synthetic division process. The synthetic division rules out any possible errors that we may make with the calculator or rounding errors. Okay, so let's continue our synthetic division process. And we have confirmed that x equals 1 is a 0. Since we got in that last spot a remainder of 0, x equals 1 is one of our zeros. Now remember, we started out with a degree 3 polynomial. So after one round of synthetic division, this result represents a degree 2 polynomial. It represents 2x squared plus 7x plus 6. If I wanted to, I could write that polynomial and factor it in the traditional way. Or we could simply continue this synthetic division process with another hypothesis from the calculator. Let's use x equals -2 because that one seems to be the most clear from the graph. We're going to confirm that -2 is a 0. Remember, we stopped short of the previous remainder. We multiply and add all the way across. And we have confirmed that x equals -2 is a 0. If I get anything other than a 0 in this spot, then it would not be a 0. Now, to finish up, our last x-intercept looks like -1.5. So we can confirm that with synthetic division, but I'm going to use the improper fraction -3/2 to represent 1.5, -1.5. So -3/2 and -1.5 are the same thing. Stopping short of our remainder, we bring down our first term. -3/2 times 2 is -3, and 3 plus -3 is 0. So we have confirmed that x equals -3/2 is also a 0. Now, just to finish out our analysis here, this would be a degree 1 polynomial. So what happens after a degree 1? This would be a constant term. So I would have 3 unique linear factors, and my leading coefficient would be right there. That might help us as a sneak preview of factoring coming up soon. For now, let's go ahead and list the zeros that we found with our calculator and synthetic division. -2, -3/2, and 1. Remember, we expected 3 zeros. We got exactly 3 zeros, which means they each have multiplicity of 1. And again, that's confirmed by the calculator by the fact that the graph crosses at all 3 x-intercepts. Okay, look what we are dealing with here. A 5th degree polynomial function. It looks big and scary and intimidating, but as you're going to see, this might even be easier than solving a linear equation. So let's make some observations. This is degree 5. So we can expect at most 5 zeros. Now, we're saying at most 5 zeros here because we mean at most 5 distinct zeros. It is possible that some of those zeros repeat, and we'd be able to see this by the behavior of the graph at the x-intercepts. So let's go ahead and type this in. This one might take a while to get typed in. A lot of terms here. Okay, so when we get our polynomial typed in, now I had changed my viewing window on the previous problem, so I'm going to type zoom number 6 to get back to that standard viewing window. We're expecting at most 5 x-intercepts. This is a pretty steep polynomial function. Notice it looks like we have only 3 x-intercepts. The x-intercept on the left would have odd multiplicity because the graph is crossing. And at the 2 x-intercepts on the right, notice the graph is bouncing. That indicates even multiplicity. We're going to be able to verify all of that with synthetic division. This time I'm going to start with the negative x-intercept, that is -2, and confirm that with synthetic division. So let's be sure that -2 is in fact a 0. So I'm going to pick up my coefficients. All of the powers are represented, so I don't have to worry about any placeholders of 0. Bring down our first term. And remember, the process is to multiply the number in the box by the number on the baseline and then add vertically. -6 plus -2 is -8. -2 times -8 is 16, and 16 plus 6 is 22. -2 times 22 is -44. 20 minus 44 gives me -24. -2 times -24 gives me +48, and -39 plus 48 gives me +9. Finally, -2 times 9 is -18. Wow, wasn't sure that one was going to work out, but it sure did. Because we have a remainder 0, we can confirm x equals -2 is a 0. So we'll keep that in our list, and let's keep up with the nature of our polynomial. That first line represented a degree 5 polynomial. So after one round of synthetic division, the result is degree 4. And again, I'm ignoring this remainder term. That's deleted if I wanted to turn that back into a polynomial. Now, let's look at the graph. Notice it crosses also at x equals 1. So let's divide 1 out of our depressed polynomial, again, stopping short of that remainder, using our synthetic division process. Okay, so by the synthetic division process, we can confirm that x equals 1 is 0. We have now arrived down to a degree 3 polynomial. Now, let's continue with x equals 1. I can tell from the graph, because the graph bounces at 1, that it has a multiplicity that's even. So that means at least a multiplicity of 2. So this is going to be a repeated 0. So I'm going to divide it out again from our depressed polynomial to show that it is in fact a repeated 0. Okay, so notice we have confirmed the same 0 over again, which means that it has multiplicity 2. The result is degree 2. We have 2 more zeros, and from the looks of our graph, it looks like the rightmost x-intercept there, x equals 3, will also be a double root. So we'll be able to confirm this with synthetic division twice. So dividing 3 from our polynomial, we have confirmed that 3 is a 0 of at least multiplicity 1, and we'll be able to confirm one more step here that it is in fact a 0 of multiplicity 2. We know that we are finished with our synthetic division process because when multiplicity is considered, we have 1, 2, 3, 4, 5 zeros. So our final result is a constant polynomial, or a degree 0 polynomial. So our zeros for this polynomial are -2, 1, and 3. But remember, 1 has multiplicity 2. That means it counts twice. And 3 has multiplicity 2. So when I sum the multiplicities, we get exactly degree 5. So again, the original problem looked difficult and intimidating, but if we understand the synthetic division process and where the information is coming from in combination with what we know about multiplicity, it was very easy to find the solutions to that polynomial equation.